All right, so in your notebooks at the end of L7, this relationship between mass and volume. Here are the key takeaways, things we got to make sure we know for our next quiz. All right, so the first thing when I was going around to the different groups, looking at your graphs, one of the things I asked some different groups was, should the line of best fit go through the origin? And as we talked about it, we decided yes. Can anybody kind of tell me why? Why should the best fit line go through the line of origin in this graph? Okay, so normally starts at 0. Well, what does the point 0, 0 mean on the graph that you guys made? What was your x-axis labeled? What did you label your x-axis? There's only two to pick from. Either you labeled it mass or you labeled it volume. Yeah. Volume. Okay? So the x-axis is volume. So if you have a point that is 0, 0, you're saying that the x value, the volume, is 0. And if the volume is 0, then the mass would also be 0. Does that make sense? If something doesn't take up any space, it wouldn't have any mass. Kind of makes sense to me too. Even if you went the other way and looked at it, if something doesn't have any mass but it not have any volume either. Okay, so the first key takeaway, if there is 0 mass, then there is 0 volume. So doing mass and volume, the best fit line should be going at the origin. Should go to origin. And origin is just 0 on the x-axis and 0 on the y-axis. Okay? Okay, so another thing we had to do was we had to calculate the slope of our best fit line. Okay, and in looking at the slope for the best fit line, the slope allows us then to make a for every statement. Okay, and what you probably noticed when you were looking at the two objects was they had different slopes, didn't they? The regular solid had one slope. The irregular solid had a different slope, and the baby oil had a third different slope. And so looking at those different slopes and making for every statements, we could see that there were different masses depending on the volume. And it changed at different rates for each substance. Okay, so what we need to understand is that the relationship between mass and volume is proportional and unique for each substance. All right, so the relationship between mass and volume is proportional. And it's unique for each substance. So this is the concept that I was kind of struggling with some of you guys. But if we're talking about our particle diagrams, and I said when you do particle diagrams, we want to show things like conservation of matter if you're doing like before and after. Or in this case, the point of our particle diagrams was to compare what would the particles in one of the objects be like compared to the other object. And so we could look at that slope and we could say, okay, so for every 1 gram, there's this many milliliters. Or for 1 milliliter, there's this many grams. But we could use that relationship between mass and volume to kind of think about our particle diagrams and what they should look like. So the third key takeaway is that the spacing between particles matters. How much space is between particles? And it matters because the relationship between mass and volume is different for different substances. It's different for different substances. Okay? So if I used a certain metal A, whatever metal A is, I might have a slope that's super steep. And then I use another metal B that the slope is not as steep. Well, that slope should stay consistent as long as I'm using the same substance, but that means that it's going to be different for different substances. All right, so the fourth and final takeaway, the key idea, the key takeaway of all key takeaways, number 4. For every 1 unit of volume, each substance will have a specific mass. We know this relationship to be called density. Okay, this is different from when I say to you guys, stop being so dense. This is the mass per volume. And whenever we say per, it's really just saying divided by. So density equals mass divided by volume. And that's why I said to you guys, man, if I had it to do over again, which I will next year, I'm sure, I would have told you guys that when we're studying this mass and volume relationship, rather than looking for the responding variable or the dependent variable to put on the y-axis, I wish we would have put mass. And I know, I forgot who answered the question a little bit ago, sorry. But they did have mass on the y-axis. That's good because then when you do rise over run, you have mass over volume, which is actually density. It was a little easier to see the relationship than if you put volume on the y-axis. Now, here's how this works if you're ever trying to figure out units, guys. Units for things. You know mass is measured in what units? Grams. So there's my parentheses and a G again. And what about volume? Milliliters, thank you. Any other units we know of? And somebody just said centimeters. Is it just centimeters or centimeters? Centimeters to the third, yeah. So we do so when we did the regular solid, we measured 3 different sides. We multiplied those 3 sides together, and we got centimeters to the third power. Because centimeters times centimeters times centimeters equals, guess what? Centimeters to the third. All right, now using the same concept when we're talking about the units for density, right, so when we look at this, if I want to know my units for density, well, in the first case, I have grams divided by milliliters. So I could have grams per milliliter, grams over milliliters. Also would look like that. That's fine. Or in this case over here, grams over cubic centimeters, or sometimes they write it like this, but same thing. Okay? So those are our units. So for density, we're doing mass divided by volume. And it's specific for each substance, and it doesn't change really. I mean, we can change it somewhat based on other factors, like if we heat something up, it might expand, and now the volume is different, but it's still the same mass. But overall, we have general standard conditions, and we can talk about that each substance is always going to have this density. There's a specific density for gold. There's a specific density for iron. There's a specific density for aluminum. All right? So, almost done here. What new questions does this lead us to now? New questions. We should write these down, of course. New questions. So, can this relationship, density, be used to answer questions? I hope so, because you guys have a big question to answer next. Thank you. All right. And the second question, is this a property of all matter? Which I just talked about, right? Okay, so those are our 2 new questions leading into L8. That's what we're working on next is L8. So you remember that yesterday I gave you guys the guidelines, kind of the outline for how to do a lab write-up, because we're going to try to answer this question. Is heavy-duty aluminum foil really heavy-duty? Again, it's like a quiz or test. Everything is done in secret at your lab table. You share your ideas with no one outside your group. The whole point is that each group needs to work together and use their brains and think. Use the puzzle part of your brain to think. All right, so that's what we're doing next. Is heavy-duty aluminum foil really heavy-duty?